Welcome to London Theory Institute lecture on CPT-symmetry in quantum field theory. So my name is Andreas Fring and I'm based at City, which is part of the University of London. And I already mentioned the topic is CPT-symmetry in quantum field theory. So here's the outline of my talk. I will start with the motivation. As always, it's always good to know why we are studying a particular subject. And then I will focus briefly on the role of PT symmetry in quantum mechanics. So PT is a subset of these transformations where the charge is not used because there we don't speak of particles and antiparticles in quantum mechanics. Then I will formulate the CPT-theorem, and I will argue within the context of Lagrangian field theory how parity, charge conjugation, time reversal act, and also I will show how this is equivalent to what is referred to as a strong reflection and the Hermitian conjugation simultaneously acting. So this is part 5, but first we have to see in 4 how they act individually. And then we can study within the context of quantum field theory various interaction terms and see how these symmetries act on these terms. And finally, I will discuss a few physical consequences. So what do we get out of this? So let's start with the motivation. Why do we study CPT symmetry? Well, one of the reasons is that it's very fundamental, and it's based on the cornerstones of physics, such as just the basic principles of quantum mechanics, Lorentz invariance, which we also believe is a very fundamental property and symmetry of nature, energy positivity, and causality. So if you study PT symmetry, CPT symmetry in some particular theory, you're also testing these foundations. And then you can also use it for model building. So if you want to build a model describing nature or parts of nature, certain effects, what you want to know is what kind of terms can you put into your Hamiltonian or Lagrangian, whatever your starting point is. And if you believe that CPT symmetry must hold, then you are already restricted to certain terms. So I will show how this works in PT quantum mechanical scenarios, and then also afterwards in quantum field theoretical scenarios when we also switch on C and have a full CPT symmetry. So as I said, you can use it to build models, and in particular what we are interested in are models that go beyond the standard model. To make advance beyond the standard model, you may suspect that there is possibly CPT symmetry and add terms to the standard model which do not respect the symmetry. And then also the study of CPT symmetry in particular theories can also shed light on the broken balance of matter and antimatter. So CPT symmetry predicts a balance between matter and antimatter, but we know that our universe is dominated by matter. So this could be due to CPT symmetry. There are other explanations as well, but certainly CPT symmetry has something to say about this broken symmetry. And then just to give you an idea that this is a popular topic and quite, well, as I already said, fundamental. So it's fundamental and popular. And if you just look at Google Scholar and you search for articles that have CPT in the title, you find 13,200 papers. That's just in the title. Of course, they might not mention it in the title, some papers, and it's still used in some way or another. Interestingly, when you study these symmetries, you are interested in the violation, in the breaking. So if you look, for instance, for CP violation, you still find over 10,000 articles. And if you just search for articles that have time reversal in the title, you find 283,000 papers, which is, of course, not just all about quantum mechanics or quantum field theory. These papers also include papers on classical mechanics, but just to give you the idea how widely this subject is studied. So let's start with PT-symmetry in quantum mechanics. And here I just write down what a PT-symmetry is, just to give you an idea. It reflects the space, and it reflects also time. And on our key quantities in quantum mechanics, it will have the effect that that the momentum, when you combine these two symmetries, just goes to itself. So below I wrote also the individual action of these symmetries. And crucially, T, and therefore also PT, is antisymmetric. It also conjugates. Yeah, this you can understand. Just think of the standard commutator X, and P is IH bar. If you send the X on the left-hand side of this commutator to minus, then somehow you have to create a minus sign on the other side, which you get from the I. Yeah, that's just a way to make it plausible. So how can we use this? So there are these various properties of this transformation. So PT is an antilinear operator. I just said this. It conjugates C numbers. So if I'm acting on a linear superposition, here lambda and mu are complex constants, and phi and psi are wave functions on which you can act. But then PT will conjugate these coefficients, as opposed to linearity, which just keeps them the same. And then there's a little statement, quite powerful, that if your Hamiltonian of the theory, I'm now talking about quantum mechanical Hamiltonians, respects this symmetry, i.e. it commutes with the PT operator, and if at the same time the eigenfunction, which you get here from the time-independent Schrödinger equation, is also an eigenstate of PT, then you can deduce that the energies of this system are real. And the proof is very simple, is one line, so I can show it to you. So just starting from the time-independent Schrödinger equation, I'm using the fact that PT phi is phi. There could be a phase, but I dropped this for simplicity here. I'm replacing phi by PT phi. Next, I use the fact that PT and H commute. So I can bring PT on the left-hand side of H. And now I'm using the time-independent Schrödinger equation and replace H phi by just phi. Now comes the crucial property that PT is antilinear, and when I pull PT through to act on the phi, it will conjugate the epsilon. And now I replace again the PT phi by phi, and we arrive at our conclusion, namely that epsilon is equal to epsilon conjugate. So this is when these two properties hold, and when the operator I'm using is antilinear. You notice I actually never used the explicit form of this transformation. So this actually holds for any antilinear operator that has these two properties as well. What happens when we break one of the properties? I will not break the symmetry of the Hamiltonian, but I do not require anymore that phi is an eigenstate of PT. What happens in this case is that PT maps some particular eigenfunction phi1 to a new eigenfunction, let's say phi2. And all these two functions have also their respective time-independent Schrödinger equations. So how are these energies related? That's the question, and that's easy to see. Yeah. If we just act with PT on this time-independent Schrödinger equation for phi1, which is written over here, and then manipulate the equation. So I'm commuting PT and H, so I bring H to the left-hand side over here. And then I'm pulling PT through, and I'm conjugating the E1. And now you see I can identify in this equation this combination PT on phi1 and PT on phi1 as a phi2, a new wave function. And therefore, I can just compare these two equations, and I see that E2 is the conjugate of E1 or the other way around. So the eigenvalues for these two wave functions, phi1 and phi2, which are connected by the PT symmetry or by the PT operator, which is a symmetry of the Hamiltonian, form in fact a complex conjugate pair. And when this happens, so let's say this happens at some point in parameter space, if I have a parameter and I parameterize the energy, and at that point where this breaking here happens, that suddenly PT does not act anymore on phi and gives you phi back. So phi is not an eigenstate of PT, then this point is called the exceptional point. It has a name. It's usually referred to as this. Yeah. And as already mentioned, PT symmetry is just an example of any antilinear operator. In all this argumentation here, I never use the fact that PT is a reflection in space and T reverses time. I never used that explicit formulation. That's just an example. It can be more complicated. And in fact, in higher dimensions, this was an example I gave here in one dimension. If you go to higher dimensions, you don't actually have to reverse all the space coordinates. So sometimes it's called as partial parity, if you like. But if you think of antilinear operators, that's rather natural. And here's the picture that summarizes the entire scenario. So we keep always PT as a symmetry of the Hamiltonian. This we don't give up. If you give this up, then you just get complex eigenvalues, and they are not related to each other in any way. So in that scenario, you think usually of decay, which are related to open systems. So if I plot now the energy, eigenenergy of H as a function of some parameter lambda, then in the orange region here, we have the PT symmetric scenario. I pick two wave functions, and both of these wave functions are eigenstates of the PT operator. And in this regime, the energies are real. Yeah, so real energies are plotted here as solid lines. And when we reach this point, which I said is called the exceptional point, then the energies become complex conjugate. And now here I'm plotting into the same plot. I'm plotting the imaginary parts as dotted lines. So over here, I'm plotting the imaginary parts. And as we argued, the energies are complex conjugate to each other, which means the real parts of these energies are now the same, as you can see here. And the imaginary parts are just reflected at the horizontal line. Yeah, so this picture summarizes what can happen in these models. So this was just about the spectrum, but of course, to have a proper quantum mechanical theory, we also need to talk about inner products and time evolution, etc. I just want to make a comment on the inner product. So if we assume here that our non-Hermitian Hamiltonian, so on this slide, capital H is non-Hermitian and small h is Hermitian, are related by some similarity transformation or the adjoint action of some operator eta, which is often referred to as the Dyson operator, then we can deduce the following. So since this small h is Hermitian, I can just take the Hermitian conjugate of this and then multiply with the eta dagger and eta dagger -1, etc. from the left and from the right, and we get this equation over here. Yeah. And I'm also assuming that the respective wave functions, the capital phi is the eigenwave function of capital H, and the small phi is the eigenfunction of small h, are related in this way. And for simplicity, we don't have to do this. I assume that eta is Hermitian. And all I want to show is now that capital H is Hermitian with regard to a new metric. So we can redefine our standard inner product by a new metric, and then this capital H, which is not Hermitian in the sense of Dirac, just taking the Hermitian conjugate, if you think of a matrix, but we need to think of hermiticity as being defined with an inner product, and we bring one operator from the right to the left or the other way around. So here is the little argument. So we redefine our inner product. So I'm just calculating here the inner product between phi and psi, and I calculate a sort of expectation value of the Hermitian operator. And that's just an example. This is true for any operator. I can place here any operator, but I want to show you that H is Hermitian. And the definition of this new inner product is given here. So this is just a notation, and this is what it actually means. On this side, on the right-hand side, this is the standard inner product, and I have to place here on eta dagger eta, but we have taken eta to be Hermitian, so I'm putting here an eta squared. That's the definition. And what I will show now is briefly, it's also a very brief argument, that we can pull the H to the other side, meaning that in this formulation, the H is Hermitian. And to do this, I use here the fact that the wave functions of the non-Hermitian model and the Hermitian model are related in this way, given by this red equation here. So I'm replacing capital psi by eta -1 psi. And also capital phi I replace by eta -1 phi. Now, since eta is Hermitian, I can just pull it over here. So the eta -1 comes to the right-hand side and will convert the eta squared into an eta. And now I'm noticing here that this is just this pseudo-Hermitian relation, this similarity transformation referred to as pseudo-Hermitian property of H. I can just use and replace eta acting adjointly on H by small h. So I get psi H psi. And now I use the fact that small h is Hermitian, so I can just pull it to the left-hand side, and it will act on the psi. Now I replace again H by eta capital H eta -1, using now the pseudo-Hermitian relation once more. And I can bring the eta to the right-hand side. So eta is Hermitian as well. So it comes over here as an eta acting on the phi. And also I replace eta -1 acting on small psi by capital psi, which is an eigenfunction of the capital H. And now I replace also the small phi by eta capital phi, and then I obtain here an eta squared. And that's just the definition of our inner product. So I can rewrite this as H psi phi. And you have seen here now that I can pull now the H from the right to the left. And that means in this metric, H is Hermitian, and I can simply open any quantum mechanics book and use the same reasoning as in the Hermitian case and show that the eigenvalues for H must be real and the eigenstates are orthogonal. You may say, hang on, but there was some breaking of the symmetry before in the spectrum. How comes they're always real? Well, that all depends now on the on the properties of the eta. So when eta is not defined properly, then this breaks down. Then this doesn't make sense. It only makes sense when you have the PT symmetry preserved. And at these exceptional points I was talking about in the spectrum, these eta will break down. So this is all consistent with each other. So we have now used this symmetry to guarantee the reality of the spectrum. And we have, in addition, a consistent quantum mechanical framework. So observables can now be constructed in the same way as over here. So observables in the Hermitian system are related to observables in the non-Hermitian system also by this similarity transformation. I will not go into more details of this, just to show you this can be used now for model building. That's the key point I wanted to make in the quantum mechanical scenario. So here's the classical examples which sort of initiated a large amount of study in this area. And it's already over 20 years old, this paper. So here's the Hamiltonian. It has a non-Hermitian potential in general. So epsilon can be any real number. So in particular, when epsilon is 1, I just get here I x to the power 3, which is truly non-Hermitian, but it's PT-symmetric. Yeah, x to the power 3 gives you, when you replace x by minus x, gives you a minus sign, and this minus sign is compensated by the fact that the operator is antilinear, so you compensate it by the I. Yeah. And you can see here at epsilon equal 1, so this is the energy against epsilon, you have a perfectly well-defined, discrete, positive spectrum over here. Yeah. You can take values in between, the same happens. And if you take, for instance, epsilon equal to 2, you may think, oh, but this is now real, but it's minus x to the 4, and that's also not a well-defined potential because this is not bounded from below. But you can see here, also in that case, we get a discrete, real, positive spectrum and is well-bounded from below. The scenario changes if you go with epsilon below 0, then you can see here that certain levels merge together and you obtain these exceptional points I was mentioning. And I suggest, and this is part of the exercises, just to try out for yourself how this works for the simple two-dimensional Hamiltonian, where the parameters here are real and the sigmas are just standard Pauli matrices. Yeah, so we talk a little bit more about this in the tutorial. So I don't want to go on about it, just to mention there are lots of applications, and a very successful one where people build or carry out experiments is in optics. And the reason is that in optics, one of the key equations, the Helmholtz equation, when you consider it in the paraxial approximation, takes on this form. Yeah, and here is the explanation of what all these properties mean. And formally, if you look at this equation, and this just becomes the Schrödinger equation, the time-dependent Schrödinger equation. If we interpret Z, which in the optics context is a dimension, as time. So this has led to an avalanche of experiments and lots of discoveries. People can realize this in waveguides. And when you are in the broken regime, which from a quantum mechanical point of view is a bit problematic because you get growth and decay, which doesn't seem to be consistent asymptotically. But in optics, people can build this, and this corresponds to gain and balance, gain and loss, which are balanced out. So that's the reason why nature physics considered here on top, you see, considered PT-symmetry in optics as one of the top 10 discoveries between 25 and 2015. And if you are further interested, there's also already a book on the subject, which I show you here. But I don't want to go on about quantum mechanics and come to the main topic now of this lecture, namely CPT-symmetry. So here's the CPT-theorem. I'll read it out for you. Every relativistic quantum field theory, and relativistic means here Lorentz invariant, is invariant under a simultaneous change of particles into antiparticles, which is the charge conjugation, reflection about some arbitrary point in space, which is the parity transformation, and the reverse of the direction of time, and that's the time reversal. And I will prove this theorem on the basis of Lagrangian field theory in this context, involving spin 0, spin half, and spin 1 fields. And we will also then look at covariant interaction terms. So the strategy is to first establish the invariance of the field equations in the interaction representation that identifies how C, P, and T will act on these particular fields, spin 0, spin half, and spin 1 fields. And then we can investigate some interaction terms. So it traces back to the 1950s. So lots of people were interested in this symmetry at the time. And the first time, I think this is generally agreed on, the symmetry appears implicitly, not spelled out too much, in a paper by Julian Schwinger in '51. And later on, people tried to prove this. And the first attempt was made by Lüders in 1954, and then improved somehow. Pauli was thinking about it as well. He found a simplification spelled out in this paper. And then the paper, I think, which is clearest, is this one by Lüders, who took this new argument of Pauli into account. And then there are more formal proofs in the context of axiomatic quantum field theory, which you can find initiated in these papers by Joost and Dyson. And of course, then people follow this up, make various modifications and so on. But I will stick to this more transparent Lagrangian formulation put forward by Lüders and also by Pauli. So what one demands here is that, first of all, the field equations remain invariant, and also the commutation relations are preserved. So here I'm listing first the relations for the spin 0 field. So it's this well-known relation over here, and the commutation relations are given here. So if I have a spin 0 field and I commute it with a conjugate at another point, I will pick up some function delta depending on x minus y. So x means here space and time. And I will say a little bit about this function, but not too much, because we just need some symmetry property of this function delta. And for spin 1 fields, we have these relations. I will not derive these relations. They can be found in most textbooks and so on. I would just use them here. And And stress now here for the spin 1 field, the main difference is this equation here, yeah. Because of the relativistic invariance. And I will use the following metric, named the Lorentz metric, where G0 is -1 and the space components, the diagonals, are just 1. So you have to watch out for this. If you change this, then of course also various things change in these equations, and in particular for the spin half field. Yeah. So here is the Dirac equation for Dirac fermions. So I will not talk about Majorana fermions. Here's the Dirac equation, and here are the corresponding anticommutators. And always, I label deliberately this function delta by the same letter. Yeah, they are different in the different theories, but they have the same symmetry in all of these theories: spin 0, a half, and 1. This field psi bar is conveniently defined in this way. So this is a row vector, whereas psi is a column vector with 4 entries, and it's defined like this: minus I is of course the square root of -1, psi dagger, and we multiply from the right with gamma 0. Yeah. And the gamma matrices have these particular properties over here, so they anticommute and give twice the metric, which implies that with our metric, it implies that gamma 0 squared is -1. As you can see here, if you put 0, 0, you get twice gamma 0 squared, cancels this out, and you just get G0, 0. And I said before, this is -1. And also we have then the properties that gamma k, where k now takes values 1, 2, 3, gamma k squared is 1. The conjugate of gamma is minus gamma, whereas the conjugate of gamma k is k. And then one usually also introduces a fifth gamma matrix, gamma 5, which is the product of all the gammas in this order: gamma 0, gamma 1, gamma 2, gamma 3, multiplied by an I. And if you use this anticommutator, you can show that gamma 5 anticommutes with gamma mu, where mu now can be 0, 1, 2, and 3 to 0. And here is just one explicit example of this delta function. But what I will be using are these symmetries over here. Yeah. So delta, and now I separate space and time. So delta vector x, these are all the space components of x, comma t, is equal to minus x vector. So I have reflected x, and t stays the same. Yeah. So it's an even function. And if I reflect time, I will pick up a minus sign. And then as a consequence, if I reflect time and space, I will pick up the minus sign here, which comes from time. And you can see this easily on this explicit form here for the spin 0 field. So this is the form. And if I just change here my limits in this interval, so it's a 3-dimensional, if I change this around, I get an integral from plus to minus infinity. And I pick up from this differential also minus sign. And then I have here a minus sign in the exponential, which I can then compensate by pushing it into the x. Yeah. So therefore, we have established the first property. And the second one is even easier if I change time, yeah, which is the x0 here. And it means I change time in both variables here in the x0 and the y0, which I have also done for the space. And then I get a minus sign here in the sign, and that of course gives the overall minus sign. And the other functions have the same type of properties. So now we demand that these equations remain invariant and that the commutation relations are not changed. And if you do this, you can define the following parity transformation. So as an operator, P acts adjointly on this field phi, and it changes x to minus x. That's what we said. Yeah, it reflects on an arbitrary point. And we also take into account some constant here. There's a constant eta p, which might appear as a property of the field. Yeah. So then we want to preserve the conjugation of this equation, and that leads naturally to this equation over here. And for the spin 1 field, we get different properties for the space components and the time components. So you see here in one case, I pick up a minus sign, and in the other case, I don't. And when we parity transform the spinors, then we have to include here a gamma 0 on the left-hand side of the psi. And on the right-hand side of the psi bar, I also have to include a gamma matrix, and I have to pick up here minus sign. And what we also demand is that the modulus of P, so these constants here in front, they were all different. For the spin 0 fields, I call them eta P, eta hat, and eta check for the spinor fields, and the modulus has to be always 1. So the adjoint is preserved, and naturally, if the fields are Hermitian, then these values, eta P, can only take values plus minus 1. And just to see how this works, I want to now show you a little calculation. You know, we don't want to check all of them, but just to see how this works for these parity transformations, I will show you now a little calculation. So I think you can see this now. So we demand that the transformed equations are the same and that the operator algebra stays the same as well. So if we have d mu is minus m squared acting on phi of x comma t, yeah. So this is just spin 0. Now we are doing this is the spin 0 equation. And if now I'm changing in this equation x, the space components to their negative, x2 minus x, then nothing will happen to these derivatives because I get a minus squared every time, and then nothing changes here. But here in the field, I have a minus xt, and that's equal to 0, of course. Yeah. So now I can multiply this equation, of course, by some constant. Nothing will change. Yeah. So I can multiply here and add here some constant eta p, and then you just see that this is simply the transform field. So the transform field, this is what we said, has to satisfy the same equation, and that's very easy to see here. Now, if I look at the commutators, that's also easy to see. If I have psi of x in t, and then I commute it with phi of y and t dash, let's say, then I have minus I delta x minus y at t minus t dash. And now I just add with p on this equation. And I will obtain here a phi minus x t, phi minus y t dash commutator. And this is multiplied also, and you see, by this eta p conjugate. And what I stated before, that the modulus has to be 1, just comes from the demand that we want to preserve this. And this is now equal to I at minus x plus y t minus t dash. And you can see here that if I now, sorry, this was, well, I've already used here the property. I can use here the property that this holds. This is what I have done here. This is not coming from the action of P. This is just coming from the property of this function here. And now I can just change x and y to minus x and y, and you see that this is preserved. So that's easy to do, and it's equally easy for the spin 1 field, which maybe I will not show now, but you need to distinguish. You have to do this calculation twice and do it for mu equal to 0 and mu equal to 1, 2, and 3 separately. What is usually slightly more involved, not too complicated either, is the spin half scenario. So let's do this. So we start with the Dirac equation. We have gamma mu d mu plus m acting on psi at x and t, and that's equal to 0. And if we write this out and use our metric, I can write this as gamma 0 d0 plus gamma k dk, where k takes the values 1, 2, 3, plus m acting on psi x t, and that's equal to 0. Yeah, so as I said, k is 1, 2, or 3. Now I change x to minus x in this equation. That means I have minus, nothing happens to the first term, minus gamma 0 d0. But if I change x, then the differentials here pick up a minus sign. So I have a minus gamma k dk plus m. And I also change here the sign of the x in the argument of psi. Now I multiply by gamma 0 from the left. So I just put here some gamma 0. And I now pull it through to the right. So I have minus gamma 0 d mu. But here I pick up a plus sign because the matrix is anti-commute. Gamma 0 minus xt. Yeah. So remember that the anticommutator gamma nu was equal to twice the metric. So if I put here 0 and k, then always the right-hand side is 0 here, and you pick up a minus sign when you commute them around. So that means I can just rewrite this now as gamma mu again, d mu plus m. And of course, I can multiply by any number I want. So I multiply now by eta p check. I have my gamma 0 here still, and here I have psi at minus xt equal to 0. And then we notice here, this is just what we stated, namely this is P adjointly acting on psi of x and t. And we have now established the fact that demanding that P acts in this way as stated over here, in this way here, as defined here, this is what I wrote down before, that will preserve the Dirac equation. So the transformed fields satisfy the same equations. And we can continue now checking also the operator algebra. And we can see that what we stated at the top will ensure that the operator algebra is preserved. So this was not a complete check. I recommend you do this for yourself of the fact that using these properties will preserve the field equations and keeps the operator algebra also unchanged. Now we can do the same for parity, for the charge conjugation. And charge conjugation changes particles to antiparticles. So we conjugate the fields. And we have to introduce also for the spinor fields. So for the scalar fields, this is straightforward. We have again these numbers that multiply the fields, and the modulus is always equal to 1. But for the spinor field, we have here some matrix appearing. A matrix multiplying. Now psi has changed to psi bar transpose, and it multiplies this from the right. So keep in mind that psi bar is a row vector and psi is a column vector. So therefore we change here a column vector to a column vector, and we have to transpose this to make sense of this matrix multiplication over here. So C is a 4x4 matrix in this case. And then similarly, you have to do something on the psi bar. When you charge conjugate psi bar, you have to multiply from the right with the C conjugate, and you transform the psi into a row vector. And C has, if you analyze now these equations, C has these properties. It's a unitary operator. And when you multiply gamma mu from the right, let's look at this equation, and then you get minus C gamma mu transpose, or whichever way you want to read this equation. And combining these properties, we also find that the transpose of C is minus C. And for similar reasons as before, these constants we multiply with, they all have modulus 1. Time reversal acts similarly. And what it means is it reverses all velocities. The idea was put forward first by Wigner in this way. And so for spin zero fields, it's straightforward. We just change the time in the phi field. In the conjugated field, we just change the time. It's slightly different, again, for the spin one field. We pick up minus signs now in the time component. So before, for parity, we picked up a minus sign in the space component. This is now reversed. And in the transformation for the spinor field, we also pick up, again, some matrix called now T, which in this case, there's no conversion from psi to psi bar. So if I want to keep this now a column vector, then I just multiply the column vector from the left with the matrix. And here I just have to do the opposite for the psi bar field. This matrix has these properties over here. And the crucial one is that it's antilinear, as we have already seen in the quantum mechanical scenario. It conjugates complex constants. So it's this property over here. Yeah, and it's symmetric. And this is the action on the gamma matrices. And again, these constants have modulus 1. We can combine now transformations. And first I want to combine just C and T. And we have seen that the adjoint action of C on gamma transpose mu gives minus gamma mu. And gamma transpose, if I solve this equation here for T, gamma transpose mu is equal to T acting adjointly on gamma mu. And if I combine this now, I just plug in the gamma T or gamma transpose into this expression over here with the adjoint action of the C, then we simply get that CT acting adjointly on gamma mu introduces a minus sign. So if I rewrite this, I multiply, there's no comma here. This is just a multiplication. If I multiply now with CT from the right, I just get CT gamma mu is equal to minus gamma mu CT. And if we bring this to the other side, we have the anticommutator. And that suggests to take CT as gamma 5, because the anticommutator of gamma 5 with gamma mu is 0. So let's proceed, and I will simplify now a bit the notation. And instead of when I act now consecutively on some operator, I will first act with the operator on the right, namely T, and I simply write it like this. So the formal way to write it is I carry out the T operation, then the P operation, and then the C operation, but we just write it in this way. And if I talk about the combined transformation, then we just write it formally. We have to write it like this, but we summarize it in this form. So some operator O is transformed to some operator O triple dash by CPT. So let's see how this works. So I have phi now, my spin 0 field, first time reversed. So I'm using now the relations I stated before, and that reverses T with the minus sign multiplied with eta T. Now I carry out a parity transformation. I reverse also space multiplied by eta P. And finally, I charge conjugate. So I have to replace this field by its conjugate and also multiply with eta C. So that's the combined action of CPT. Same for the spin 1 field. I reverse the time, multiply by this constant. When I time reverse, now I'm acting with P, which picks up a minus sign here in this case and reverses the space. And when we charge conjugate, we have to replace this field by its conjugate field. There's no hat over here. When we do it for the time component, we pick up a minus sign in the time reversal. We reverse also the argument. And now we act with P, we reverse the space. There's no additional sign coming here. Always we multiply by these constants as well. And now I charge conjugate, replace this field by its conjugate. And at the same time, we also have to multiply with some eta. Finally, we do the transformation for the spinor field as stated above. So if I time reverse the spinor field, I would reverse the T and multiply the spinor field by the matrix T. Now we carry out the parity transformation, which multiplies by some eta, again, eta P in this case. and we reverse the space, and the charge conjugation carried out at the end will replace the spinor by its adjoint, and also we still have what I didn't mention here, the parity transformation also introduces here the gamma 0, and then we have the CT. And as we said before, CT we can identify as gamma 5. And similarly, you can do this carry out these separate transformations for the conjugate fields. And the summary is here in this box over here. Yeah. So I also replaced here CT by gamma 5. And here is the transformation which I did not show you for the conjugate fields. And crucially, we have to note also that CPT is antisymmetric. Yeah. So if some terms are multiplied by some constants now, then and they are complex, then we have to conjugate them as well. So that's the summary of how CPT, when acting adjointly in this order, how they will act on spin 0 fields, spin half fields, and also spinor fields. So for the spin 1 fields, you see here, despite the fact that in between we pick up minus signs in different ways. So here for the spin 1 field time component, we pick up a minus sign from the time reversal, whereas for the space component, we pick up the minus sign from the parity transformation. But in the end, there's an overall minus sign. So in this blue box, I combined them again together. So the point is now that this is actually the same CPT transformation. This part of the CPT theorem. This is the same as a simultaneous reflection of time and space, which was introduced by Pauli and referred to as a strong reflection, and a Hermitian conjugation. So first I will look at the strong reflection, demanding again what we demanded before, that the field equations and the commutators are preserved. And when you go through this analysis, as I argued before, and I suggest we do this in the tutorial, or you do it at home by yourself, then this will guarantee that these equations are preserved. These transformations will do this. So I have reversed time and space now simultaneously, but at the same time, you have to do what we have seen in detail before. You have to multiply these fields, sometimes by some matrices and sometimes by some signs. Yeah. So in this case here, we pick up minus signs for the spin 1 field. The spin 0 fields are just staying the same. They're just reflected. And if we reflect just time and space for the spinor fields, we also have to multiply by I gamma 5. So to guarantee this, you have to have these fields ordered. Yeah, you have to symmetrize your interaction terms with respect to bosons and fermions, and that amounts to a Wick ordering. It just means you symmetrize your expression completely, depending on, of course, you have either anti-commutators or commutators, depending on what type of statistic you have. So this is sort of giving you also the deep connection to the spin statistics theorem in a loose sense. But the problem here is that what I didn't read out yet is that you also have to reverse the order of the field operators. So that's a bit tricky. Yeah. This you can do when you act on an operator algebra, but you can't do it in Hilbert space. Yeah. So you can't really apply this strong reflection to Hilbert space. But the next operation will do the same, and then this problem is solved because this compensates each other when you do this transformation simultaneously. And that's the Hermitian conjugation. So if we just conjugate now fields, so we simply replace spin 0 fields by its conjugate, spin 1 fields by their conjugate, and spinor fields by their conjugate. That's the operation. But of course, conjugation, Hermitian conjugation, changes the order of operators. Yeah, here it's just for the fields, but if we have product of fields, then the order has to change. Yeah. And also conjugation, of course, conjugates numbers. Yeah. So lambda goes to lambda conjugate if that appears somewhere in the term I'm acting on. This psi conjugate is just conveniently written into the adjoint spinor transpose multiplied by gamma 0 from the right. That's just the definition used for the adjoint spinor. And if we summarize this now together, we combine now these transformations, strong reflection and Hermitian conjugation, then this is what we get. Yeah. So a spin 0 field is just replaced by its constant with reversed arguments x and t, space and time go to their negative. Spin 1 fields pick up a minus sign, and spinor fields pick up multiplication by gamma 5 times gamma 0 onto the adjoint spinor transposed, and also the arguments are reversed. And then similarly, the adjoint spinor transforms like this. And inherited from the conjugation transformation, this is also similar as in CPT, namely that the constants go to their conjugates. But while each transformation reverses the order, this is now compensated, and in the joint transformation, the order of all operators remain the same. And in the combined transformation, you also have that lambda goes to its conjugate. And crucially, now this transformation can be applied to the operator and also to the Hilbert space. And what we can see now, if we compare this now with what we had before, so if we compare this blue box with this blue box, the combined CPT transformation and the combined transformation of strong reflection and Hermitian conjugate, we see that this is absolutely identical if we take the products of these constants to be 1. Yeah, so in each of the cases, if you we always had these combinations appearing, the product of all these 3 different constants, then for each of the fields, the spin 0, a half, and 1, this product is taken to be 1, and then the combined CPT transformation is equivalent to the Hermitian conjugate plus the strong reflection carried out at the same time. That's the heart of the CPT theorem. And if we demand now the invariance of the interaction term, they have to transform in this way. Yeah. So if I have an Hermitian interaction term, then the CPT transformation, or equivalently the action of strong reflection and Hermitian conjugate just changes the argument of the Hamiltonian. So since it's Hermitian, we just see the strong reflection, namely x is changed into minus x and t is changed to minus t. But it's not just a strong reflection, because that would also reverse the order of the operators, which is not the case here. So then the theory said something about relativistic, meaning Lorentz invariance. So you can just consider Lorentz invariant terms and include them now into your interaction. So here are some examples for the spin half fields. Other examples now you want to know how does this transformation act on interaction terms of different kinds. And here's another example. If I compose a tensor out of derivatives of the spin 0 field and the spin 1 fields, then these tensors under CPT will transform in this way. They change the arguments to minus. I combine now x in t into just x, and I pick up, depending on how many factors I have here, I pick up a -1 to the n. Then one would like to see bilinears of Dirac fields. How do they behave? And we see here a term like this. So it's Hermitian, psi bar psi is easily seen to be Hermitian, and under CPT, it transforms as follows. We have to change. I'm just using now what we have written down before. So I'm just using, this is the same as CPT. So this is what I'm using here. So psi bar goes to psi transpose at -x, gamma 5, gamma 0, and psi goes to gamma 5, gamma 0, multiplying gamma bar transpose at -x. And then we see here that this product here is actually just 1. Gamma 0 and gamma 5 produce a -1 when I conjugate them. Gamma 5 squared is 1, and gamma 0 squared is -1. So this minus coming from the conjugation is compensated, and we see that this transforms in this way. And since it's Hermitian, we also just observe the fact that we have seen this over here as well, that Hermitian fields transform under CPT just in the way of replacing the arguments, namely x and t, by their negative. We can look at other terms, other bilinears. So here's, I'm putting here a gamma 0 in between, and also I'm including here an I. So what happens to this transformation? To this term, when we transform it, first of all, you can check that it's Hermitian, and then we transform with CPT, and we see now that we pick up here a minus sign from the I. We replace the gamma bar by the psi bar by psi transpose at -x. We have to multiply by gamma 5, and then since CPT conjugates numbers and also matrices, we have to replace this here by gamma 0 bar conjugate. And from the replacement of the psi, we get the gamma 5, gamma 0 psi bar transpose also at -x. And then we can change now, this is the transpose. If I change the order, then I can transpose it, and we get the product in the right order again. And this is the result. Similarly, we can transform psi bar gamma 5 psi, which transforms. So again, we can convince ourselves of the hermiticity. We transform it now by replacing again psi bar by psi transpose at -x, gamma 5, gamma 0. Gamma 5 has to be conjugated. Here's a typo. This should be a gamma 5 here in this matrix. So it's a gamma 5 conjugate. And on the right-hand side, I have replaced psi by gamma 5, gamma 0, gamma bar transpose at -x. And again, we use the algebra of the gamma matrices, and we commute this through. Gamma conjugate 5 is gamma 5. So therefore we get a 1 here, and then we get a gamma 0 times gamma 0, which is -1, and that compensates this minus sign here in front, and we have a gamma 5. So what about separate transformations? When we just carry out them individually now on interaction terms. So it has been shown that QED and QCD are invariant under separate C, P, and T transformations. You don't need to combine them into CPT. You can carry them out individually, and the theory will be preserved. But chiral interaction terms, they violate individual C and P transformations. But when you combine it, these two transformations into CP, then chiral terms remain invariant. So let us see how this comes out. So I'm writing down here some chiral interaction term. Psi bar, gamma mu 1 minus gamma 5, psi a mu. And we just want to check now the charge conjugation. And I'm simplifying the notation even further. And I also ignore now the arguments. So we understand now that on the left-hand side, we sometimes have x. And on the right-hand side, it might be minus x minus t. Nothing changes here when we have charge conjugation is also x and x on the left and right-hand side. So let's carry out the charge conjugation. And I replace here the psi bar by eta c, psi t conjugate, and then the c conjugate gamma mu c. This comes now from the right-hand side, gamma bar transpose, and the a goes just to a. And in one of the transformations, we picked also up the minus sign. Yeah. So all I'm using is now is these transformations over here, which we defined here. So we are using these transformations here, and you see here when we replace the psi bar, we pick up this 1 minus sign. That's what I was trying to highlight. So here we are. So this is the equation we get, and of course here we have again eta c conjugate is 1. And then we have argued before that C conjugate acting on gamma mu, C is minus gamma transpose mu. And now here they are all transposed, this product. So if I reverse the order, I can get rid of the transpose. And I have also compensated here these two minus signs. And you see this has been left invariant under charge conjugation. But if we look at the other term in the chiral interaction term, namely this one, it will transform in this way. Yeah, I don't read this out now anymore in detail. We have done this now a few times. Just comment on the calculation that follows. So we insert here between gamma mu and gamma 5, we can insert a 1. Yeah. And then we can carry out C conjugate gamma mu, or the adjoint action of C. But it's also the conjugate, it's not strictly the adjoint action. C adjoint multiplying gamma mu C, and the same action on gamma 5. And from the gamma mu action, we get a minus gamma mu transpose, and the gamma 5 is just transposed with no sign over here. And then we have all transposed here. We change the order, and these two minus signs are compensated, and we get this expression over here. But now the difference is that the gamma 5 is on the left of the gamma mu. So to convert it into the expression we started with, I have to commute the gamma 5 and the gamma mu, and we pick up a minus sign here. So this term is not invariant under charge conjugation, and therefore the overall chiral Lagrangian interaction term is not invariant under charge conjugation. If we do now the same for parity, so parity, we look at the first term. Now under parity, A picks up a minus sign. This minus sign came from the transformation. And here, so they compensate, and I have also already here commuted gamma mu and gamma 0 and put this gamma 0 to this side here. Yeah. So this minus sign is now compensated by gamma 0 squared, which is -1, and then we end up again with the same term we started with. So again, the first term is invariant under P. It was also invariant under charge conjugation. And now we do the second term, which transforms in this way under P. And again, I have already commuted the gamma 0 to the left here of gamma 5 and gamma mu, which gives 2 minus signs. So therefore, there's just a plus. These 2 minus signs compensate each other. And then we have here gamma 0 squared, which gives us a minus sign. And now we see again that this term is not invariant under P because of this minus sign over here. Yeah, it transforms into the same, but with an over minus sign. So the chiral interaction term is also not individually invariant under parity transformations. But you can guess already what comes next. Yeah, we just combine them now. P and C combined will compensate the minus signs we pick up in each of the individual transformation, and therefore under CP, the chiral interaction term remains invariant, but not individually. Okay. So one can, of course, now investigate all kinds of other interaction terms just in the same way. This is how you transform the fields, and this is the logic you can now apply to different terms. And you would start with good candidates are Lorentz invariant terms, unless for some reason you want to break Lorentz invariance, and then see the effect C, P, and T have on these new terms. What are the physical consequences? Can we measure this? What happens when we have now a theory? So first, people to point out that one has to be a little bit careful to draw conclusions. So we now make experiments and we want to check is CPT conserved or not. And CPT predicts equal lifetimes of particles and antiparticles, and also equal masses. So, but one has to be careful drawing the conclusions, because if you observe equal lifetimes, that can mean that either CP or CPT is valid. That this was first pointed out by Lee and Young in this paper. And if you observe experimentally different lifetimes, then you can, however, conclude that both CP and CPT are violated. So one has to be careful in one's conclusions when one makes experiments. And a famous experiment was carried out in the 60s that shows CPT violation. So here is this sort of logic, how you would go about it. And the violation appears in the decay of neutral kaons. So there are two types of K-mesons, K and K bar 0. Yeah, they have both spin, but they have opposite strangeness. And therefore, so they're different. They're assumed to be complex scalar fields. Phi 1 and phi 2 are the components, and they conjugate to each other. Yeah. So this is what one assumes to be the general structure of these fields, K0 and K0 bar. Now, if you work out the CPT action on these two fields, you will find that CP is, they are not eigenstates of the CP operator, because CP changes the wave function of K0 to the wave function of K0 bar. And in reverse as well, CP acting on phi 0, on phi bar K0, sorry, the bar is in the wrong place, it's a phi K bar, gives you phi K0. So therefore one defines some new fields made up now of phi K0 and phi K0 bar. In one case you take the sum, in the other case you take the difference. These are just normalization factors you put, but the key point is that now what you find is that these new fields are eigenstates of the CP operator. So CP acting on this new field phi K10 gives you phi K10, and CP acting on K20 gives you minus phi K20. So what has been observed also is that K-mesons decay into pi mesons. And what one can calculate, I will not do this here, is that the wave function made up of a pi plus and a pi minus is an eigenstate of the CP operator. And the wave function of a triple product, namely of pi plus with pi minus and pi 0, picks up a minus as well, like phi K20. So what would CP preservation mean? Well, in this decay process, it should be preserved. It should be the same before and after the decay. And that means that K10 decaying into pi plus and the pi minus would respect the CP symmetry. You see here, there was a plus here and a plus here. They have the same PT symmetry. And a K20 decaying into pi plus, pi minus, pi 0 would also respect CP symmetry, because in both cases we pick up a minus sign. These two minus signs are picked up on the left and on the right hand side, before and after the decay. But in 1994, in this paper, Christensen and other people, they observed this process. The K20 decays into a pi plus and a pi minus, which clearly violates CP, as one can see here. In one case you have a minus, and in the other case you have a plus. So CP is violated in this process. So this was the first observation of CP violation. So while CPT is assumed to hold in all processes, the individual transformations and even combinations such as PT, they can be violated. As a consequence here, if CP is violated, then also time reversal must be violated in this process, right? And then the combination will again compensate, and we expect this to be CPT-symmetric. Okay, that was my short lecture on CPT-symmetry. I will conclude with some references. Some of them are already mentioned, so I just go over them just very briefly. So this is the first paper by Schwinger there CPT appears indirectly for the first time. Here's the first attempt of a proof by Lüders, which is okay-ish. One can read the paper, but I think the clearest paper is this one over here, which uses the argument of Pauli already and simplifies a bit the proof and the argumentation as well. Here's an interesting paper I didn't mention before. It's about methods of testing the CPT theorem, thinking about experiments, etc. And these two papers I also briefly mentioned already. These are treatments of the proof in a more formal setting of axiomatic quantum field theory. Yeah, so this is more formal and more rigorous, doesn't use Lagrangian description, but just uses the axioms, general axioms of quantum field theory. And then you can find these transformations in essentially any good book on quantum field theory. So I thank you very much for listening, and I see you for the tutorial, and we discuss a few more details.